Trying to find the TDA 2050 version of this board I made. I need it for my video. Where could it be? Look at all this stuff. I don't think it's in this pile. Stuff falling everywhere. Well, I'll have to come back when I find the board. Okay, now I found it. It was sitting on the heatsink, still connected to the heatsink from the video when I was demonstrating the TDA 2050. So now I can carry on with the subject of the video, and that is 10% distortion figures. Why do they use these silly 10% distortion figures? I've seen this question come up a few times, so I thought I'd answer it, do a demonstration, and also show you how you can get the real distortion figures of the amplifier. Here is the TDA 2050 datasheet from my October 1991 SGS Thomson Microelectronics. That's back when they were still using SGS in their name. And it says preliminary data. So this is before the chip actually came out. Of course, now it's been discontinued. But anyway, let's see here. 35 watts, true RMS power. Oh, there's that RMS again. Into 4 ohm load at total harmonic distortion equals 10% with the supply voltage plus minus 18 volts, 1 kilohertz. So what does that mean? Does this mean it's a bad amplifier? It has so much distortion? No, not at all. It just means they're propping up the numbers so they can get a higher wattage figure. What they're doing is they're pushing the amplifier into distortion. You see these figures a lot on some car audio ICs, car audio type gear, and some home electronics, amplifiers and things like that. Cheaper ones, I mean. Proper home receiver will have the FTC type rating, which of course will be much better. But yeah, it's just a way to prop up the numbers to make the wattage look good. So if we skip back into the data sheet where they have the graphs, you'll have some distortion versus power and distortion versus frequency type graphs. Not all data sheets have it, but most of them will have at least a distortion versus power. So if we look at this one, they're showing with a 4 ohm load, they have a couple curves for different frequencies. And this line here is the 1 kilohertz line. And you can see that it's pretty low, 0.03, and it starts shooting up. And it goes up because, of course, the amplifier is going to hit clipping. Doesn't matter if you have a cheap amplifier or a $10,000 audiophile amplifier. You know, if you hit clipping, it's going to distort. And of course the THD figures are going to go way up. So if we look here, you know, this is 0.03 at 24 watts. And this curve here is at 15 kilohertz, and it's higher, but still it's under 1%. It's down probably around 0.4%. Solid state amplifiers are always going to have higher distortion figures at higher frequencies. That's just how it works. A better design amplifier would definitely have a lower, higher frequency distortion curve. For example, the LM1875 has very good distortion at higher frequencies. It's a better chip in my opinion for hi-fi use. But we're using the TDA 2050 because they have the ridiculous 10% distortion shown on their datasheet. This datasheet also shows distortion versus frequency, and you can see the amplifier is doing pretty good here. Now, it depends on your circuit layout how it's actually going to perform. If you have a very bad layout in your circuit, you're not using the proper star grounding, you may not be able to reach these numbers. And in some cases you can actually beat these numbers because a very good layout, better than what they used to test this chip, you can actually beat those numbers. Most audio gear rates their equipment at 8 ohms, and with this IC, this is the 8 ohm reading, and it's very good. It's just a $3 chip, and it's doing very good. They're testing at a supply voltage of plus minus 22. The other one was at plus minus 18 with a 4 ohm load. But yeah, you can see that the distortion is very low, dipping below 0.1% for most of the power range here, and then of course it starts to clip and it's going to go up. Okay, so now let's actually do a demonstration using the IC. We'll measure it at pre-clipping, and then we'll measure it at 1%. When you get into 1% levels, you're talking about the amplifier starting to clip a little bit. And then we'll also measure it at 10%, and we'll compare those numbers. Okay, so I have the little amplifier hooked up to the power supply, plus or minus 18 volts. It's just sitting idle right now. This is just a jumper connection board. These items here are not part of the circuit. Going into the little amplifier from the music player. Okay, as usual, we're in the spectrum analyzer mode on the scope. 1 kilohertz fundamental, 4.5 kilohertz 1% pilot signal. So I need to show 10% on here, and this is showing 2 gradicules, so I need to turn it down, this 1%. So now it's at 1/2 of a gradicule, so I can crank the amp into clipping. So we need, that'd be 2, 4, 6, 8, 10%. And we're getting a big third harmonic spike. It's third harmonic because it's clipping on the top and bottom. So that would be indicative of symmetrical clipping. And there's not really any other harmonics except for that. Maybe a couple small notches. And those, they'll add into a little bit of the total. So we'll just eyeball it, set it a little bit less, and we'll just call that 10%. So I'll turn this signal back on, and you can see it's clipping. And I'll get a measurement. Now I have to use the scope's RMS figure here. I cannot calculate RMS directly from the peak-to-peak value, which you would normally do on a scope that can't display RMS. The reason being is because it's clipping, it's not a sine wave, and you can't use the normal calculations. They wouldn't work. So thankfully the scope gives us an RMS value, and we can use that to figure the distortion. So what we do here is take our 12.3 volts RMS squared when we're running a 4 ohm load. 37.8 watts is the power we're getting at 10%. So I'll note that down here. Okay, so now I want to get distortion at 1%, so I turn that down, turn this up, and I just want to match the distortion level with my reference. And well, we got a few peaks there. You just can't add these up. It's more complex mathematical equation to add all of those peaks up, those harmonic peaks, to get the percentage of distortion. But what I'm doing is just eyeballing it here, and we'll say this is about 1%. Of course, that's my reference again. So we'll see what kind of distortion we're getting here. So you can see what clipping looks like at 1%. It's very minor, but it's definitely there. Okay, so if I didn't say so before, we take 11.1 volts RMS and square that divided by 4 ohms. That gives us the power. That's 30.8. So you can see going from 10 down to 1%, how we lowered the power. So now I'll measure what I call the maximum clean power before clipping. So I'll turn all those harmonics away so there's nothing left. Right about there is good. So all we have is our reference signal. All the harmonics are gone. Let's see what kind of power we're putting out. 10.7 volts. Okay, so at below measurable distortion, we're putting out 28.63 watts. Alright, I had to change the battery in the camera. I need a better solution. Maybe like a webcam, something that I don't have to depend on batteries for video shooting. But anyhow, what do I mean by below measurable distortion? Well, my oscilloscope, it can measure down to 0.2%, 0.3% reliably. If I had better equipment, I could certainly measure the actual distortion that the amplifier is making. So in summary, at 10% distortion with the amplifier well into clipping, we're getting almost 38 watts. That makes the numbers look nice and high compared to just 28.63 watts before clipping. In other words, there's not any significant distortion. So yeah, they're just propping up the power figures of the amplifier by using that 10% number. To me, it doesn't make sense. It makes the chip or amplifier look bad when you do that. I would rather see pre-clipping figures like this. Well, hope that helps you out. And thanks again for watching.